All right, thank you, and hi again. This is a really quick overview of Viper. Uh, Velta is inspecting Polar Exploration Rover. That's what Viper stands for. I apologize to all those people out there who've seen these slides umpteen times. It has heritage going back to Resource Prospector. And so, yes, a lot of the slides are reused. Really what Viper is about, though, is understanding lunar water at the poles and understanding it at scales that are important to both exploration and science. And those are the scales at what I call the human scale down to the meter scale. And to do that, you really need to get at the surface, to the surface, and actually need to get to the surface with some level of mobility as well, as I'll explain here a little bit more. Ultimately, Viper is an exploration mission. It is out of the Planetary Science Directorate, however, and so it does both science and exploration. Where it lives in terms of its goals is shown on this chart here. As an exploration mission, we're really interested in understanding the resource potential of volatiles, namely water, for the most part, at the poles of the moon. And we need to do that before we can actually ever understand what the potential reserves are at the moon in terms of water. So we need to better understand at the proper scales the distribution of water and volatiles in general, both laterally and vertically. We need to understand the form. Is it molecular hydrogen? Is it ice versus bound water, et cetera? But also we need to understand its context and correlation. And this is really important in terms of getting at its accessibility, understanding how to create predictive proxies for the water, things that we just don't have now, that allows us to actually determine whether or not it is a reserve. And this is really where this mission differs from a traditional planetary science mission, is its intent on doing applied science to determine water reserves at the moon. Ultimately, we need to understand the distribution, the form, and the context. And because it's a resource exploration mission, it is actually borrowing very heavily from what we do here on Earth in terms of economic geology, resource exploration, and mining applications. We really do need to sufficiently characterize the area to understand the resource and whether or not there is ultimately a reserve. Just defining the word reserve for the moon still needs work, and it's not exactly what that means. And this mission actually takes the first steps to do that. It's important to distinguish randomly walking around and looking for resources, as I got the old prospector up here with the mule. That's relying on hope and luck. Ultimately, we're taking on the processes and the tools and the experience that terrestrial exploration systems use and applying that science to the moon, looking at both summary statistics, understanding variability phenomena using various geostatistical approaches, and ultimately making predictive surfaces that are indicative of the total potential yield of a particular area and the confidence in that yield. And that's what you have a figure down the lower right here shows the exploration map for Alaska for a particular set of mineral types. And ultimately, this is what we need for the moon to understand the potential yield and our confidence or certainty in that yield. Ultimately, though, it's important, this is where just exploration and science crossover critically is to do that well, you need to have a handle, an understanding on the emplacement and retention of the water. This allows you to build what I call a resource model. On Earth, we call it a mineral model. It actually uses both the empirical statistical models and theories, but also the theoretical models to create a predictive map with much better confidence. And that's ultimately what we intend to do with starting with Viper and following on with missions that will come after it. So the Viper mission is a rover mission. We need that mobility. It's about a 350 kilogram class rover, so kind of MER class. It's entirely solar, and that is done to keep it relatively low complexity, low cost, and so it can be done quickly. It's to meet some of the goals of the Artemis program. We need to get up there very fast, very soon, and really get to this exploration now. So we're keeping the first missions solar. However, that said, we found clever ways to actually extend the mission at the summer poles to multiple lunar days. So this is a difference from Resource Prospector, which was meant to really just live a single lunar day. This can live 3 to 4 lunar days by finding what we call safe havens, areas that have less than 96 hours of darkness. We can survive that and live on to the next day to continue exploring. A very interesting and novel aspect of this project also is that it is being delivered by Eclipse commercial contract. So you've heard about the Astrobotic and Intuitive Machines commercial landers. A task order will be going out for Viper to the same set of Eclipse commercial providers to land Viper on the moon. So this is exciting in that it will bring those Eclipse providers into the 300, 400, 500 kilogram class landed capacity, which for all of us having that kind of access to the moon, that kind of payload is really exciting. This is a quick project timeline. We're looking around FY23 or so for launch. So to do this, one of the key spatial proxies we're relying on is temperature. You know, temperature is important for ice stability. It's not alone the sole requirement, but it is important. So we organize our mapping in terms of understanding what we call ice stability regions. These are 4 ice stability regions that we've defined working with ISRU technologists to determine the breakoff between 50, you know, where we define deep and shallow. But they essentially take a look at ice stability depth maps that Matt Ziegler and Dave Page have developed and describe them in terms of surface stability regions where the ice is stable at the surface, shallow where it's near the surface, in the top 50 centimeters it's stable, deep where it's stable between 50 and 100 centimeters deep, and then dry is basically where we expect it to be too warm to be stable. We do this to help us organize, again, the operations, the mapping, et cetera. And this, it gets back to actually building coherent resource maps that we can use going forward. In each of these ice stability regions, that we need to characterize it at a variety of scales. And I won't get into it here, but there's a lot of thought that's gone into this and analysis that's gone into this. But ultimately, it comes down to the two processes that are really probably governing the heterogeneity of volatiles at the surface. That's impact gardening and temperature. And so within any one of these ice stability regions, this kind of square I've drawn here, we need to understand the variability, the heterogeneity across that at the scales we think it will be variable. Right now, we think it's variable at the scales of tens of meters because that's the kind of the density of impact craters that excavate down to a meter deep. So we need to do that. We need to understand the heterogeneity at those scales, but we also need to understand what a total area might yield. This is important to the ISRU folks. Both of these are, how do I mine it and how much do I get out is basically what A and B will let us know. And then finally, C is what is the consistency or the variability across one ISR, one ice stability region, to the next ISR of similar type. And that basically allows us to really build or develop a level of confidence in ore grade correlation across thermal and geological contexts. We're using 4 instruments to do this. Viper is really a reconnaissance mission. It's meant to be light and move and move and move, meaning cover as much ground as possible. So we, from Resource Prospector, we leaned up the payload, lightened it up. It has these 4 instruments, a neutron spectrometer that you just heard Rick Elphick talk about, a near-infrared spectrometer system, which you heard me talk about, a mass spectrometer developed by Kennedy, Janine Captain's the PI. It's a quadrupole mass spec. And then also a drill named Trident, from Honeybee Robotics that Chris Eckney is leading. What's really exciting about Viper is these three instruments, the neutron spec, the near infrared spec with the imager and temperature measurements, and this mass spectrometer are on continuously, always on while roving, always on while drilling. The intent is they are on all the time, and it's going to create this great continuous data set for us. The Trident drill is a 1 meter drill, and in each science station, we will drill at least 3 times to 1 meter, looking at those cuttings every 10 centimeters to build a profile of volatile content with depth. Where we're going is kind of summarized in this chart here. Because we want to survive that 96-hour dark period, we've identified the regions where the longest period of nighttime over the summer, the 4 months of summer, is only 96 hours or less, and that's what's shown in these yellow pixels here. So there's quite a number of places we can go with that requirement near a range of ice stability regions. I'll show you a traverse plan focusing on this one here, which is near the crater Nobile. This is the crater Nobile here. In the next slide. This shows a typical traverse at Nobile. The yellow areas are these safe havens again, where you have less than 96 hours of darkness. What we do is we land and we can run out on one of these traverse paths, exploring the area, performing a variety of drilling activities and mapping activities at various science stations, and then returning back to one of these yellow areas, these safe havens, to survive the short lunar night, that 96 hours, but also we park it there while the Earth sets. We are in direct to Earth communication all the time. That's how we operate. So we need to park and stay still somewhere safe while the Earth sets for 2 weeks and comes back up. Just for scale, each of these inner circles here have a radius, or outward radius of 100 meters. So this is 500 meters, this circle. This is 1 kilometer, 2 kilometers, and 3 kilometers. So you can see this is a 4-day mission where we drive out. Each one of these little petals of the flower is a single day. This is the final day where we drive out to 3 kilometers and die a glorious death out here in the shadows. Some statistics for this particular traverse, and this is somewhat typical of the kinds of missions we're looking at, is about 91 days of operations, up to 20 kilometers of total traverse distance, visiting 6 PSRs, 24 science stations. Each one of the science stations has drill sites. We're looking at about 40 drill sites overall. So this is really a great improvement over what we were looking at for RP, getting much more data, especially the number of drill sites is greatly expanded. So
Tony's giving you a warning. You're coming up on the end of your time slot here.
And this is my final slide. So perfect. I'll leave it there. Thank you. Yep. So we all know it's about time we got back to the moon and did some of this stuff, looked at these scales. And so Viper is the first of a number of exploration missions that are needed to really understand the water reserves at the poles of the moon. Thank you.
Thank you. There were a couple questions in the chat that I'll ask quickly while we are switching over. We can switch the sharing now over to Mark Robinson. But while we're doing that, there was a question. Tony, do you know, or anyone online know, if SMD will support a participating scientist program for Viper?
I am very much pushing for that and am optimistic that they will. That it will be very important. So we recently just moved to planetary from LDEP and have started those conversations already. So I'm going to fight for that as best I can.
Okay, and then 2 more quick questions, both from Clive. For Viper, have you considered Peary Crater? And then I think this is a rhetorical question. Viper is the first in the prospecting campaign, right?
Absolutely. So yeah, so depending on the pole we go to, yeah, we've looked in the past up near Perry, and our site selection timeline real quick is right now we're still again using the site analysis and traverse planning to help develop the rover and ConOps. By CDR, we'll have a site selected, but between then and now we will have actually a community workshop on site selection and traverse planning to get community input and vice versa on it. So we're open to any number of sites that meet the criteria, within the design requirements. And then, yes, I am making it clear that this is a reconnaissance mission that ultimately leads to future missions to identify reserves. Exploration science is an iterative process. It's not a one-off and you know exactly where to drill. And it's a matter of risk. It's what our customers want to accept in terms of risk.
All right, thank you so much.